In this video, we are going to work with a problem where we have a mass balance and a heat balance that interacts. We are going to have the example where we have ammonium nitrate, which is a solid, and we put it into a reactor tank, and we then solubilize it into ammonium ions and nitrate ions. This dissolving of the ammonium nitrate actually absorbs some energy from the solution, and we call this enthalpy the enthalpy of the solution. We could also, in this case, call it enthalpy of reaction. It will do the same thing in our math and in our coding that we will get to in a moment. When we have a reaction that absorbs energy, we call it an endothermic reaction. And we have a mixer in our reactor that ensures that the mixture is always completely homogeneous. We pretend that we add 500 kilograms per cubic meter of this ammonium nitrate to the reactor, and we have a starting temperature of 323 degrees corresponding to 50 degrees Celsius, and we have a working volume of 1 cubic meter. Let's get into Python to start and code it. So we will first start by writing some of our known constants. For instance, the starting temperature, we call it T0. The start concentration of ammonium nitrate, 500 kilogram per cubic meter. We then have the enthalpy of reaction. We call it HRXN. That is 25,700 joules per mole. Already now I would like to convert this heat of reaction to joule per kilogram. So the molar mass of this compound is 80.04 grams per mole, and we can then calculate the HRXN. Kilograms is equals to HRXN divided by the molar mass, and then divide this by 1,000 to get it in kilograms instead of grams. Let's run this to start with. Good. We also need the volume of the system, which is 1 cubic meter. We need the density of the water, which is 1,000. And we need the heat capacity of the water, because it will be the water that will absorb the energy or that will give the energy away to so the reaction can occur in this case. The unit will here be in kilograms per joules per kilogram Kelvin. Right, so when we have a heat balance and we have a mass balance, it actually just corresponds to having two state variables, just like when we had different compounds in our solution. We could have reactant A and reactant B. We had two state variables, but the heat balance is just another state variable. So we make our initial condition array. We say this is just, if we want the mass balance, we have to have the concentration times the volume of the system. And the second state variable, that is our temperature. So these are the initial conditions. Now we are ready to define our rates function. So we always have t and y. We have v rho Cp and H Rxn. Good. The first thing we can do is to make it a little easier for ourselves. We extract the state variables from our y. So the mass of A is the first state variable in y, and the temperature is the second one. Then we need to calculate the reaction rate. So that is equal to R. We assume it's a first order reaction times Ca. So we need to calculate Ca, the concentration of the compound A, but we only have the mass of A. So we need to say Ca is equals to Ma divided by the volume. And we also have not passed K to our function yet. We will do that uh, by actually defining two other constants we call A, which is some Arrhenius pre-exponential factor, and we need Ea, which is the activation energy. Let's pick this number. Like this. Alright, so we can calculate what the rate constant is equal to based on the pre-exponential factor A and the activation energy and the temperature of the system, because the rate constant will depend on the temperature, and that is the important thing in this coupling of the mass balance and the heat balance, that the reaction rate depends on the temperature. So there is an equation that looks like this. And this equation describes how the rate constant develops with temperature. It will always increase the rate constant when we get to higher temperatures. Yeah, there's an error here, and that's because we have not defined R, and R is equal to joules per mole Kelvin. Good. So now we have what we need in order to make the derivative of the mass. So that would be dma dt, that is equal to R, because we have no flow of mass going into the system or mass going out of the system. It's a batch reactor. We only have the reaction. And because the reaction is right now in units of uh, kilograms per second per cubic meter, therefore we need to multiply it by the volume of the system. But in this case, the volume is 1 cubic meter, so it will not make a difference in this case. Now we get to the heat balance, or the energy balance. The energy balance normally looks like this. We have M times Cp times dt over dt. But in most cases, we are actually not interested in the energy. We want to know the temperature. And we are also giving the temperature as the state variable input. So it needs to be the dt without the m times Cp on the left side. So we will write it like this instead. And here we will have the Q Rxn uh, and that will be calculated in a moment. And that is the energy absorbed or released by the reaction. And because we had CPM on the left side, we divided it over, so it stands here now. But first, now we have to calculate QRXN. So that will depend on the heat of reaction, HRXN, which we have already here, so we just have to say, and then times the reaction rate. And the reaction rate is still per volume, so we multiply by V to get the complete energy release or absorption in the whole system. Good. M is not defined, and we can calculate M. That is the mass of the system it's in. That is equal to the density of water times the volume. And now we have the two state variables derivatives here, dma dt and dt dt. We will return it, an NP array. And here I can just use the NP array because we have a 0D model, whereas in contrast to the 1D modeling, we used NP concatenate here because we had 1D arrays of these. We still have to choose a maximum simulation time, let's say 1000 seconds. Then we can write our solve IVP. And our initial conditions, I think we call it Y0. Yeah. And let's say we want to have 100 time points in the output. Lastly, we need to put in all the arguments that our rates function need. That would be, and we have to use the same order also. The first two ones we don't need to pass in there, but the rest we need here. And then we can run everything. We can make a plot, time versus the first state variable. And it will be in seconds, and it will be, that will be kilogram. Let's try to plot that. Right. So we start at 500 kilos of the ammonium nitrate, and then it's solubilized over time, almost reaching 0 kilos left after 1000 seconds. What about the temperature? How does that behave? Copy the code here, and the other state variable, that will be temperature. We can kind of confirm this by going into the solution here. Oops. And see, the second row here, that is all the temperature data. Up here is the concentration or the mass data. So let's plot that. In a new one. And of course the unit will be temperature in Kelvin. So we see that the temperature also drops over time. That is because the reaction takes out heat of the system. It requires heat to run. That also means that the more this reaction occurs, the slower it goes because it takes out heat, which reduces the reaction rate because K depends on temperature. With lower temperature, you get a slower rate constant, and with a lower rate constant, you get a slower reaction rate. So if you leave such a reaction for a long time, it will eventually stop, maybe even before you have converted all your reactant.